Welcome back, scholars, to Mr. Honeycutt's math class. So now we're going to take all those factoring skills and use it to graph and interpret quadratics, and then we're also going to apply it to rationals. And hopefully you'll see how this all fits together. Now, the IB and the ACT both have a bit of a love affair with the quadratic equation, and they really want you to really understand the quadratic equation. And the IB in particular wants scholars to understand the quadratic equation in this very great depth. So there are various forms of the quadratic equation. This is sort of the standard form, all right, the ax squared plus bx plus c. There's a vertex form, which we're going to start using a lot when we get to transformations, where this is the vertex, is the h and the k, and then the a tells us the vertical stretch or compression. And then there's factored form of the quadratic equation, where we're just splitting the quadratic form into factors, like we've been practicing all day. And then remember, there is also this a, if you don't quite know what it is. So there might be a constant multiple out there or a negative or something like that. But yeah, so these forms are useful for different things. So I just want to I want to take you through an example, show you what the forms look like and are. So here, the standard form of this quadratic right here is, for the ax squared plus bx plus c, it would be x squared minus 8x plus 7. The vertex form of the exact same equation, all right, the vertex form would be x minus 4 all squared minus 9. Notice there is no a here because the a is an implied 1. Oh my gosh, yes. And then the factored form is going to be x minus 1 and x minus 7. Now, one of the things that's sort of nice about the standard form is that the y-intercept is always equal to c from the standard form. So in this case, it's really easy to see on the equation. So it's easy to see that the c is a positive 7. And then if we go over here on the graph to the y-axis, the y-intercept, hey, look at that, the y-intercept is a positive 7. So the standard form is easiest to see graphically, the y-intercept. The x-intercepts are easiest to find in factored form because I just set the factors equal to 0, okay, because the output is 0 on the x-intercepts, all right? And then I can use the zero product property to set these each equal to 0 individually, all right? And whether I have the parentheses or not doesn't really matter. So add 1, add 7, x equals 1, and then x equals 7. So my x-intercepts are, according to the factors, x equals 1 and x equals 7. Notice it's literally, you just solve it mentally or quickly, and then 1 and 7, and then, hey, look at that. Hey, there's my x-intercepts right there. Notice, by the way, you could also go backwards for both of these. So that with standard form, you could go backwards and say, you could look at this graph and not knowing anything else about it, you could say, okay, I don't know anything about this, but the y-intercept is c. All right? I don't know anything about this, but these are the factors, which we've done that. We've practiced that a little bit. Now, the axis of symmetry is the line that the vertex goes through. And all quadratics are symmetrical. So in this case, the axis of symmetry, the thing that cuts it exactly in half, is the line x equals 4. Okay? That's a vertical line, equals x equals 4. And then the vertex is this bottom point right here. And it is the point for negative 9. And as you can see, vertex form, again, because we're math people do not creatively name things, all right? Vertex form is the form that gives you the vertex. Factored form is the form that gives you the factors. Oh my gosh. Very efficient. So here is this, and it's got that minus thing, so that like whatever's inside, you actually have to flip the sign. All right, we're going to study that a little more in depth soon, like what's going on with that, in case if that always has bugged you. But yeah, that's the vertex form. So different forms, I hope you can see, reveal different things about the graph. So that the axis of symmetry and the vertex are revealed by vertex form. That standard form gives you the y-intercept. and that factored form gives you is easiest to find the x-intercepts. Also, I want you to notice what's happening right here. All right? Notice that this is 1, 2, 3 units away, and then this is 1, 2, 3 units away. So the vertex, the axis of symmetry, is actually the midpoint of the x-intercepts on the quadratic. This is only on the quadratic. It has to do with the symmetry of the quadratic. So if you're actually going to go, we're going to see soon of going between different forms, but I want you to point out this midpoint. Now, you could have figured this out other ways, but that's actually the easiest way. So, just kind of want to talk briefly about standard form versus factored form versus vertex form. Okay, and these are 3 different equations, all right? Don't think they're the same thing. Now, each form, there are certain things that are easier to do, and there are certain things that are harder, sometimes even impossible to do. And so that most of the time, why we want you to be able to algebraically jump between these forms is because so that you can do the things that are easiest to do in that form. So in the standard form, okay, it's pretty easy to evaluate. It's very easy to determine in behavior. You just look at the leading coefficient. Okay, it's really easy to find the y-intercepts. Okay, and you will learn in calculus that it is ridiculously easy to do calculus procedures. All right, like you will be able to do them in your head. No one believes me, but you will. All right. What's hard to find from standard form is the x-intercepts, positives or negatives, like intervals. It's hard to interpret for calculus, which is strange. The procedures are easy. The interpretation is quite difficult in this form. And then transformations are quite hard in standard form as well. In factored form, it's almost the opposite. Notice what was hard in standard form is easy in factored form. Because you factored it, it's pretty easy to find x-intercepts. It's pretty easy then to find positive and negatives. You make a little sign chart. And it's pretty easy to interpret stuff for calculus in factored form. Okay, determining in behavior is a little tricky. Evaluating can be a little tricky. It's just a little different actually than this one. And but it's still pretty doable. Finding the y-intercept is a little hard. It's kind of like evaluating, and then doing calculus procedures is actually quite a bit more difficult in this form, which is kind of ironic. So interpreting is easy in factored form for calculus, but doing the calculus is tricky. Now, vertex form. Obviously, what's easy is finding the axis of symmetry. You just take the h, and it's x equals h. So in this case, it'd be -1. Okay, finding the vertex. That's just there's your h in your k, so it's -1, -5. And then transforming again in vertex form, we'll see is actually quite easy because it's already in the transformed version, the parent function of, if you will, of it for transformations. Calculus is actually not too bad, but it's not as easy as the standard form. And basically in vertex form, everything else is hard. So the main reason why we want to be able to jump between these forms is like, what are you trying to do? Like, are you trying to do something that's easy in that form, or are you trying to do something that's hard in that form? And often the easiest way to do these harder things from various forms is just to switch to a different form. So I made this chart to help you understand how to switch between forms. All right. So if we're starting in standard form and I want to find x-intercepts, I'm going to want to go to factored form. And then obviously the way to get to factored form is to factor, all right? But if I want to figure out like a y-intercept, if I want to do calculus, it's actually generally going to be easier to go to standard form by distributing some way. Okay, we call that foiling, but factored form can also work with polynomials, not just quadratics, and that holds true. If I'm in standard form and I want to go to vertex form, I'm going to have to do that process called completing the square, which you should all be familiar with from Algebra 1 and Algebra 2. But that's one of the main purposes is to go from standard form to vertex form, because it's easier to graph. Once you found the vertex, it's quite easy to graph it. And then for vertex form, to go back to standard form, I'm going to have to distribute as well. But remember, it'll be like an x minus h squared plus k. You've got that a, so really that's x minus h times x minus h plus k. So you'd have to, that's what I mean by that kind of distribution. There is a formula for that, the squaring formula, but remember, it's not just x squared minus h squared. No, 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 no. All right, that's a red card. All right. Now let's say we're in factored form and we want to go to vertex form. Well, the easiest way to go to vertex form from factored form is to find the midpoint, as I said. You'll just find the factors, and then the midpoint is going to give you the axis of symmetry, and then from there you can just plug the axis of symmetry value into factored form, and it will give you the y value, which would give you the k. And that's basically the easiest way to do that. Now, if you forget that, you could just go back to standard form and then complete the square. That'll work too. And honestly, I thought about this. I don't think there actually is a way to directly go from vertex form to factored form. I could be wrong, but maybe in some unusual cases. And if somebody has something that knows about that, that'd be great. But yeah. So this is how you need to know which form does what, which form is most helpful, and then how to get between them, because that's going to give you like what to do. So for instance, if they give you standard form and they want you to find the x-intercepts, you say, hey, I know that the x-intercepts are easiest to find in factored form. That means I need to factor. All right. If they give you factored form and they want you to find the vertex, that means you need to think, hey, I need to go on find the midpoint between them. All right, and then use that to find the vertex. Or I could also go to standard form and then there at a vertex form. So just kind of, that's what we're doing with all this. And notice you actually, if you're going from just an algebraic equation to a graph, if you're going to graph it by hand, that you're going to basically need to do all three of them. So just looking at this, given factored form, and IB really loves giving factored form and then asking you to do things with it that are unusual. So finding the roots in factored form is, again, really, really simple. You just set it equal to 0, and then you use the zero product property so that you're, so x minus p equals 0, x minus q equals 0, and then x equals p and x equals q are x-intercepts. Now, finding the y-intercept, you would have to multiply everything out. You can do that. We can do that with variables, but it ends up being the last term. It's going to be this times this times this, and a negative p times a negative q is going to make a positive pq, and it'll also have the a. So the x-intercept in this case is actually a times p times q. All right, finding the x-coordinate of the vertex. Well, we're going to need, remember, if I'm going from factored form to vertex form, I'm going to need the midpoint. All right, well, I have the x-intercepts. That's nice. So all it's going to be, the x-coordinate of the vertex, I'm just going to take p plus q, and I'm going to add them together and divide by 2. And that's going to give me the x-coordinate of the vertex, which is also the axis of symmetry. Okay. Now for the vertex itself, this axis of symmetry we can also think of as h, the h value in the vertex form. So what I'm then going to do to find the vertex, because I got to then find the k value for the vertex form, and that's going to be equal to, I'm going to have to plug it in to this equation for my x value. So it's going to be like my midpoint, x value minus p times the midpoint minus q, and then whatever this a is, and I'll plug all those in, and that's going to give me the k value, which is the low point, the minimum for the quadratic, or the maximum. That's how I'm going to have to basically plug it back in. All right. So then my vertex form would then just be the y equals a x minus h squared plus k. All right, and having found the k, I just plug those in. So the algebra here, this probably looks nastier than it actually is. Like literally with numbers, you're just, once you found the midpoint, like that would be 4. And then in this case, like the previous one, would be like 4 minus 1 and then 4 minus 7. and then I would multiply those together times the a, which is 1. All right? So both of those end up being 3. So it ends up being 9, negative 9. So the standard form you're going to FOIL. The official name of FOIL is double distribute. So, and I think taught you how to use the box method for that. So, all right. It's kind of a high level view of that. Now, the quadratic formula, how does the quadratic formula come into all this? There's a couple of ways. One, I want you to think of the quadratic formula as, you can think of this, but I think it helps to actually distribute the division here. And so that we're actually thinking of this as negative b over 2a plus or minus the square root of b squared minus 4ac over 2a. And if you're looking at the graph, all right, like that one we had, okay, what this actually, if you remember, what's nice about this, if you remember the quadratic formula like this is your axis of symmetry. All right, that negative b over 2a. That's the thing that's going down the middle. Okay? And then what this piece of the quadratic formula is telling you is actually the distance between that sort of axis of symmetry and the x-intercepts on either side of it. They're on equal and opposite sides, so one is plus that amount, one is minus this square root of b squared minus 4ac over 2a. All right? But it's this amount right here. The other thing that's special that you need to know about the quadratic formula is the discriminant. I'm going to talk in a little bit about the discriminant, what it means, but you need to be able to interpret it and what it means, and especially oftentimes on, like, say, the IB test, every once in a while on the ACT, they'll give you scenarios where it'll be like a quadratic only intercepts the x-axis once, solve for this other variable, and what they're actually doing, you have to understand that when they're giving you that clue, that's a discriminant clue. What the discriminant tells us is how many times the quadratic, the parabola, intersects x-axis. And we can tell that algebraically just from analyzing the discriminant. I'm going to talk about that soon. But so notice this midpoint stuff, the quadratic formula, you notice how this stuff is probably a little more interconnected than you've ever realized. And the IB especially is going to demand that you know and understand that, whilst the ACT, your scores will go up if you understand that and all those little connections. So talking about the discriminants, okay, the b squared minus 4ac, the stuff that's under the square root. Basically, when the discriminant is positive, when the b squared minus 4ac is positive, I'm going to have two x-intercepts. I think that's a c. All right, so notice if I do a b squared, that would be 6 squared minus 4 times my a is an implied 1 times 5. So that's going to be 36 minus 20, which is a positive 16. Hey, look at that. It's positive, therefore I'm going to have two x-intercepts. Now, if the discriminant equals 0, all right, so this is the positive. This is the discriminant equaling 0. There's only one x-intercept. Okay, just one. So notice if I do the b squared is 6 squared minus 4 times 1 times 9. Well, that's going to be 36 minus 36. Hey, that's 0. And it's telling us 1. So notice this is a bounce. It only touches it once. So that's telling us it's a bounce. So back to that example, if the IB says something like there's only one solution, and sometimes they'll call this is sometimes called a double solution or a double root or something like that, because there's two. This is actually easy to then put in factor or vertex form. So this would have the form, by the way, x plus 3 squared. And so notice it's a double. There's no k. The k is 0 in this case because it's on the x-axis. Now, so positive 0, so guess what this one is? It's negative. Okay? So when my b squared minus 4ac is less than 0, when it's negative, all right, there are no x-intercepts. Okay? So that b squared minus 4ac, that's going to be 6 again, squared minus 4 times 1 times 11. So that's going to be 36 minus 44, which would be a negative 8. Hey, that's less than 0. That's negative. All right, that tells me there are no x-intercepts. And then what that means, this is where, if you're taking, since this is going to be negative, that means that I would then be taking the square root of a negative number. And that's why the solutions are imaginary, because the solutions there's no real solutions. The quadratic doesn't actually touch the x-axis. So that's what creates imaginary solutions on these. So that's the discriminant. So what it can tell us from standard form about the graph. So yeah, notice that's pretty easy to find from standard form. Is easy to go to the discriminant to find this information. Now, the fiche de resistance, putting it all together. All right. So I've got, as we started all this stuff, I want to be able to factor, and this should have been a review. Like most of this stuff you've seen before. I'm probably connecting it deeper than you've seen before. All right. But that's it. We're just taking everything you've done like in Algebra 2 and like really pushing it up. I know that the pace of material probably feels pretty intense in this lesson. It feels like a lot, but you really have done all of this before, sometimes for several years. So from this form, the first thing I'm going to want to do is I'm going to want to determine in behavior, because I want to be able to sketch. Remember, that was our initial thing. I want to be able to sketch the graph of this without worrying about it. So I'm going to determine the end behavior. So I don't really care about this stuff. All right. All I care about is this. Hey, that's going to kind of cancel out. So my end behavior, I'm going to have a horizontal asymptote because it's an eats DC at y equals a -1. Because remember, there's implied ones here. All right. Then the next thing I'm going to want to do is I'm going to want to factor. Okay. The first thing I want to do out of the numerators, I'm going to want to factor a -1. Notice that they're all negative. So, and then that'll give me x squared plus 5x plus 6. I'm going to use my factoring rules then. So my c is positive. They're going to both, and this one's positive. It means they're both going to be positive. So then what multiplies to 6 and adds to 5? So that's going to be 2 and 3. So that's going to be an x plus 3 and an x plus 2. And then I'm going to factor this. Hey, that's difference of 2 squares. So I should be able to do that automatically. X minus 2, x plus 2. Now, so that's factored. And then I'm going to find the x-intercepts, removable discontinuities, and vertical insert. Those are holes. You actually want to find the holes first. I probably should have put that first. So notice that these two factors are the same. That's when you're multiplying and dividing by the same factor. So that's a hole. So there's a hole at x plus 2 equals 0. So then you're having 0 divided by 0, so which is x equals -2. All right. Now for x-intercepts, all right, I'm going to solve the numerator. What's left over, what's not a hole, so that's just going to be the x plus 3 equals 0, which is x equals -3. And then for the vertical asymptote, I'm going to take the denominator. So that's going to be x minus 2 equals 0, which would then make a vertical asymptote of x equals 2. So those are my 3 pieces. Then I'm going to want to make a little sign chart. All right, I don't need to worry about the holes. I do need to kind of graph something there. I'll show you what that looks like. But I'm going to have a vertical asymptote at 2, and I'm going to have an x-intercept at -3. I also know from my end behaviors that it's negative on either side. So this is going to be negative, and this is going to be negative, which means this is not a bounce. It's just a single factor. So this is going to be a plus. Same thing over here. So now I've got a sign chart here, and I've got all the little pieces that I need to be able to graph this. So I'm going to go ahead and graph it by hand. So, and I just left everything up here. So first I'll probably draw the horizontal asymptote at -1. Okay, then I'm going to draw me a y-intercept at -3. And then I'm going to draw me a vertical asymptote at 2. All right. And I know from my sign chart that it's going to be positive here, but negative here. And it'll be positive. It'll be negative on this piece right here. It's going to be positive in this region, and it'll be negative here. Okay, so I'm going to start. This one's probably going to be the easiest one to draw. All right, because I know I've got to hit the 0, and it's going to have an x-intercept, so it's going to probably look like that. All right. And then it's going to, the vertical asymptote's going to be going up this way. So it's probably going to look like this. So I'm going to curve it towards. And I want you to remember that there's a hole at x equals -2. So we're going to draw a little hole right there, just to signify where the hole is. And then I'm going to, so this is positive, so then this will be negative. So it's going to look something like this. Not perfect, but. And that's going to give you a pretty good, pretty accurate sketch of what the function looks like. And we drew it by hand, and we understand what's going on. So that's where we've been aiming. Basically, the whole purpose of all this has been to make you into a human graphing calculator. And while you're like, well, but I have a graphing calculator, you can make a picture of it. Yeah, here's the deal. You need to understand why the graph is doing what it's doing, so that you can then transform things and figure out how to make your equation match your data. That's ultimately where we're going. You have to be able to understand like how to make the graph, because then knowing how to make the graph helps you interpret the graph. So, all right, that was a lot of review. You have lots of delta math, but it is review. So you're just kind of pushing it up to a higher conceptual level, really, really working on those factoring skills that are always, always useful, believe it or not. And yes, so get to work on that delta math. You have plenty. Can we fix everything? No, but we can fix something today.